So today I want to tell you about black hole microstates, by the way. But before I do that, I want to derive for you the temperature of the torsional black hole. I'm not sure whether I'll get through everything I want to get through today, so I want to make sure I at least give you the heuristic picture of what's going on. So someone could please stop me around 9:45. I'll just give you a sketch, big picture, for black hole microstates going. So I was pedantic, and I wrote expressions with H bars and C's in the past. I will no longer do that. The reason I did that was I wanted to emphasize the quantum nature of temperature and entropy. Now that we've made that point, I don't think it's necessary to belabor it. So C equals H bar equals 1. And I want to tell you about a nice, simple derivation of the Schwarzschild black hole's temperature. So in order to do this, let's recall a fact from statistical mechanics. Relation between statistical mechanics and quantum mechanics is a thing I want to recall. So we know the partition function, the canonical ensemble, is the sum over states, e to the minus beta times the energy of the state. Beta is the inverse temperature. So we can write this as sum over states which is summing over the quantum, all the states in the system. And this guy is the trace of e to the minus beta h. Right? So suppose we were going to look at the path-integral picture of quantum mechanics and consider the propagation from an initial state to a final state. The propagator is going to be k at position q prime. And then we evaluate this after a time minus I beta, starting at position q and time 0. So my time here is imaginary. Okay? So when I do this, I evaluate q prime e to the minus IH minus I beta, because that's the time, q. This is the initial state, propagating, and then I look at the overlap of the final state, q prime. So I'm going to insert a complete set of states here. I have q prime, e to the minus beta h, sum on states j, 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 q. Okay? So I just insert the identity here. And e to the minus beta h extracts the jth eigenvalue for the energy when it hits this. Because I'm looking at a complete energy eigenbasis. So this equals sum on j, e to the minus beta ej, q prime j, j, q. Okay? These are just numbers. And I can flip the order at will. And let me set q prime equal to q. And let me integrate over all the intermediate states. Over all the states in the system. So k, q, minus I beta, q, 0 equals integral of e to the minus beta ej. So this equals sum, actually. Let me put things in a slightly different order. With the sum on j of j integral dq q q j. Okay? But this just equals, so this is also 1. So this just equals sum on j e to the minus beta ej, which equals the partition function z. partition function of a statistical system is the same as a path interval when we take time to be imaginary. Okay?
And if K prime is not, if Q prime is not equal to Q?
If Q prime is not equal to Q is a different thing I'm computing. So, the partition function of a statistical system and the propagator for a quantum system, the fundamental objects in both theories are the same thing. You're just interpreting time as an imaginary quantity. Now, in quantum field theory, we can make similar statements. We just use the propagator in quantum field theory, which is related to the action. So, in quantum theory, we can recast the previous expressions as trace e to the minus beta h equals the integral dq, path interval d phi, e to the minus s Euclidean of phi, where that's the Euclidean action for your system. So Q is a boundary condition on phi. So we have phi of beta equals phi of 0 equals Q that we integrate over all the possible boundary conditions. So the periodicity in Euclidean time is identified with the inverse temperature beta. This is quite similar to what we saw in quantum mechanics. Okay? So let's remember the Schwarzschild metric. The Schwarzschild metric was ds squared equals minus 1 minus rs over r dt squared plus 1 minus rs over r inverse dr squared plus r squared d omega 2 squared, where rs is 2 g-Newton times the mass. Okay? So, let me perform a change of coordinates. Let me write z as r minus rs. And let me work in a limit where z is much, much less than rs. This is a near horizon limit. Because I'm zooming in close to the horizon of the black hole when I take this limit. Okay? Let me also fix this angle on the S2, because the angles on the S2 are not going to be relevant. So we just let me choose a particular beta and phi on the omega 2 and write the metric in this limit. The metric is approximately minus z over rs dt squared plus rs over z dr squared with corrections order rs numbers. Okay? Let me then stare at this expression for a bit and be modestly clever. And let me define a new variable. My new variable is going to be something I'm going to call rho squared. And rho squared equals 4rs times z. So make the change of coordinates. And let me express things in terms of kappa, the surface gravity, which is 1 over 2rs. When I make this change of variables, ds squared then is minus kappa squared, rho squared, dt squared, plus d rho squared. Okay? So this looks very much like a metric in polar coordinates. So let's just Wick rotate t to minus I t Euclidean. And this then becomes plus kappa rho squared dt Euclidean squared plus d rho squared. Okay?
So, sorry, but what's the argument of the solid angle?
So I just fixed angles theta and phi here. So this term's going to not be relevant, so I just want to ignore it. So let me fix the angles, so d omega has a d theta and d phi factor, which are 0. So this is the metric now in coordinates where I've Wick rotated. I look at this metric, and I notice that this kappa te is an angle. And the metric is just the metric of polar coordinates if kappa TE lies between 0 and 2 pi. This tells me then that Euclidean time has a periodicity of beta, which is equal to 2 pi over kappa. And plugging in the value of kappa, this equals 8 pi g Newton times the mass. Therefore, the Hawking temperature is the inverse of this, since it's 1 over 8 pi g Newton m, which is what we claimed for Schwarzschild previously. Okay? Everyone happy with that? Okay, so now that we've explored a bit about the Schwarzschild black hole, I want to change to a different black hole. So the Schwarzschild black hole is a very difficult black hole to analyze the entropy of. We don't know how to do this even in string theory. We've got some vague suppositions, but nothing concrete, for how to get the entropy of the Schwarzschild black hole. So let's look at a different black hole. Let's look at a supersymmetric black hole in 5 dimensions, or 6 dimensions, if you like. So we're going to consider BPS states in string theory. BPS states saturate some inequality. As a result, they're extreme little solutions. They don't decay. Their temperature is 0, in other words. So my discussion here is going to be based on a paper by Samir Mathur, a review article by Samir Mathur, kappa TH 0502050. I'm going to look at various charged black holes in string theory, and I'm going to try to interpret what their statistical mechanics might be. So for specificity, I'm going to work in what's called type 2A string theory. Type 2A is a critical 10-dimensional string theory. It's a theory of closed and oriented superstrings in 10 dimensions. And the 2 means there are 2 space-time supersymmetries. And the left movers and right movers transform separately under these symmetries. And these left and right movers have opposite chiralities. That's what type 2A means. So if that doesn't make sense, just ignore what I said. It's a particular class of 10-dimensional string theory that building objects in. Okay, so in type 2A string theory, there are what are called fundamental strings. There are other solitonic objects called NS fibranes, Nebu-Schwarz fibranes, and there are p-branes, Dirichlet p-branes, for p even. That's the, these are the tools we have in order to construct solutions in type 2A string theory. Now, suppose we have a compact circle. So y is the same as y plus 2 pi times some radius r. Okay? And suppose I take a fundamental string from string theory and wrap it around a circle. I can wrap it around the circle with some winding number. Okay? So when I do this, so the winding number, I'll call n1. Okay? When I do this, I can write down a metric for the space-time generated by winding the string n1 times around this compact circle. I'll just write the metric down. The metric looks like ds squared equals h1 of r inverse minus dt squared plus dy squared plus sum I equals 1 to 8 dxi squared. Okay? So this h1 is equal to 1 plus q1 over r to the 6th, which equals e to the minus 2 phi, where phi is a dilaton. Okay? So this r measures distance in these coordinates. Okay, so r is equal to r squared equals xi, xj, delta ij. So, let me look at the limit where r goes to 0. Where r goes to 0, h1 blows up. So this factor, h1 inverse, this goes to 0 in this limit. Right? So, in this limit, the dilaton, so we're taking a limit where r goes to 0, the dilaton phi goes to, so phi is equal to minus 1/2 logarithm 1 plus q1 over r to the 6th. So the limit where r goes to 0, phi goes to minus infinity. So the type 2a we can think of as a limit of M theory. And in M theory, this F1 string is an M2 brane. This M2 brane wraps this y direction, but it also wraps another circle, the R10 circle, associated to the limit in which type 2a obtains from M theory. Because the dilaton is going to minus infinity, this M2 brane, which has tension, is collapsing the y cycle and the R10 cycle from M theory. So as a result, because these factors are vanishing in the metric, the horizon has 0 size. So classically, the entropy of this horizon is 0. So in this, so this is what I want to emphasize. In this setting, horizon size vanishes. So we're really not measuring a macroscopic entropy in supergravity in this limit. So this isn't the perfect black hole for us to study. We're building our way to a nicer black hole to study. Okay? So I don't expect all of you to understand all these details. I just want to sketch out a story for you. So the story is that if you take these fundamental strings and wrap it around a circle, you get some metric. This metric morally looks like a black hole metric. Okay? However, because of the various factors, these harmonic functions which appear in the metric, having particular behavior in the r goes to 0 limit, this metric, it turns out, has a 0 horizon area. So it's not a good black hole for us to study classically in this picture. So one thing we could do is add extra charges. So we're constructing things not just out of F1 strings, but out of other objects in the theory as well. Okay, so this is, if you like, the one-charge black hole. So the next thing to study is a two-charge black hole. Any questions? People at least vaguely happy with the story, even if you don't get the details.
Sorry, so if there's 0 horizon, that means there's no black hole, right?
Well, it means the black hole horizon sits on top of the singularity, if you like. So there is still a black hole.
Okay.
It's just a 0 horizon black hole. Now this fundamental string has vibrations in these these 8 directions. This is 1 goes to 8, not infinity. In these 8 directions, we have vibrations. So 2 to the 8th is 256. So if you like, the entropy scales like log of 256, which is just a number. So even in a large n1 limit, this remains log 256. So the entropy is really tiny. It doesn't depend on the charge at all for this one-charge system. Okay. So for the two-charge system, let's consider the space-time, which is S1 cross T4 cross R5. Or R1/4 if you like. So S1 is just a circle direction. It's the same circle we had previously. But this T4 is a 4-dimensional torus. So here, let's wrap N1 strings on the S1 as before. But let's also include N5 and S5 rings that wrap S1 across T4. Okay. When we do this, the metric is ds squared is h1 of r inverse minus dt squared plus dy squared plus the sum a equals 1 to 4 dza squared plus h5 of r sum I equals 1 to 4 dxi squared. So these ZAs parameterize the torus. Okay? And H1 and H5 are 1 plus Qi over R squared. The dilettante this time, the 2 phi is the ratio of H5 over H1. So as phi goes to 0, as R goes to 0, the dilettante this time is finite. So it's not going to minus infinity. Dilettante works out to be phi equals 1/2 log Q5 over Q1. So we're in slightly better shape than before, but again, the R goes to 0 limit, this collapses. Okay? So again, the horizon size is 0 with a 2-charge black hole. So let's go one step further and include a third charge. The third charge is just a momentum along this circle. You have a momentum and you can have winding for the fundamental string on this circle. When we do this, we include a momentum charge into the game. And as a result, the horizon is ds squared equals h1 of r inverse minus dt squared plus dy squared plus k dt plus dy squared plus sum a equals 1 to 4 dza squared plus h5 of r sum I equals 1 to 4 dxi squared, where now, again, we have dilettante is either the 2 phi is h5 over h1 again. hi's are defined as before, but now we also have k, which is qp over r squared. So now, because of this cross term, the circle no longer shrinks to 0 size. So the entropy here, so the horizon area here, is finite. Okay, so this is a good black hole in the sense that it's got a finite horizon area in supergravity. Okay? And we want to interpret this horizon area as encoding for us an entropy to construct the number of states specified by this area, and then try to see whether we can make a microscopic description of what the entropy is actually counting. Yeah?
Could one just have included the momentum charge, but not the NS5 ring to get a horizon?
So if we included N1 and NP instead of N5, again you would get a metric which is horizon, which has got 0 horizon area. You need 3 charges turned on in order to get a finite horizon area. You can pick any 3 charges you like. It turns out these charges, as we'll see, are related by dualities. So it's just a choice of basis, if you like, that I pick these charges in this order. Yeah?
So I'm struggling to figure out how a black hole can still have a singular.
So think about a singular space-time. So these space-times are singular and R goes to 0 set. So suppose you put a horizon just on top of the singularity. That's what I mean by 0 horizon area.
want to understand not the details of the calculation, but the story about some kind of integer gives us rise of matrix because the one number is integer, right?
Yes.
So because you said that integer
So,
gives us the matrix.
This Q1 is going to be proportional to that integer n1. So it's in the metric.
Sorry, Vishnu, what does it mean having a zero horizon, a horizon that is vanishing? Does it mean that the distance between the singularities and the horizon is also zero?
Yes. It means the horizon sits on top of the singularity. It means classically, the entropy is zero. This is. Now, if we include what are called alpha prime corrections in string theory, the Volcar showed that you grow an area. So you're no longer working, say, in supergravity with the Einstein-Hilbert action. You're working in supergravity with alpha prime corrected action. So you include higher curvature terms in your action. When you do that, even the two-charge black hole has a finite horizon area. Okay? Yeah?
What do you mean by one charge?
So remember the curve solution was a rotating black hole. It had a parameter J, angular momentum. So here, I've got a single parameter Q1. If I think of this more or less as an electric charge.
Sorry, and did I understand correctly? So the entropy is proportional to the winding number.
Entropy is proportional to the area of the horizon. Okay, so what am I doing for time? No, okay. So I want to at least make a couple of, I want to compute the area for this guy. This is complicated by the fact that the metric I've written is a so-called string frame. And when I compute the area in an Einstein frame in order to get the area which corresponds to the horizon of the black hole. So I don't want to go through the details of this calculation. It's a bit messy, and it's easier to do on paper than it is on a blackboard. But I want to indicate a couple of things you need to keep in mind when you compute areas, so or entropies in general. So essentially, the entropy is area over 4g, where g is a Newton constant. We've seen the Newton constant is different in different dimensions. So what Newton constant do I mean? And how do I compute so area is entropy is area over 4g. So which g goes here? Now, in string theory, we're working in 10 dimensions. So G10 is 8 pi to the 6th GS squared alpha prime to the 4th. So GS is a string coupling. It tells you the strength of the string interactions. And alpha prime is a string scale. It tells you the length of the string. Alpha prime is the length of the string squared. So this G10 has got units of length to the 8th, which is what we expect for G10. Okay, so G4 has got units of length squared. So the dimension of G10 is 2 dimensions. The length dimension of this coupling is 2 less than the dimension of the space-time. Okay, so this has got length 8 because alpha prime is length string squared. So G5 is the coupling constant we want to put in here. This is a 5-dimensional black hole study. So what's the relation between G5 and G10? It turns out that the relation is G10, but with a volume of the compact directions. So this is a useful formula to keep in mind when you're computing things in string theory. You want to compute the Newton constant by taking the 10-dimensional Newton constant and dividing by the volume of the compact directions. Okay? So if you work through the derivation of what the area is in Einstein frame, you'll find that the entropy turns out to be S black hole equals 2 pi square root n1, n5, np. Okay? And this is basically just computing the area here in string frame, multiplying by a factor of the dilaton to move to Einstein frame, and then dividing that by G5 in order to get this quantity. Okay? So some mechanical procedure you follow in order to get the entropy. This is a gravitational calculation. This is computed from a metric. So this is the gravitational side. We want to see if we can construct enough states to account for this entropy. Okay? That's the goal here.
Sorry.
Yeah.
So if one has to compactify differently, that leads to another different charge, then is that always leading to maybe black hole?
Well, I mean, it depends on your setup. So I've chosen a particular setup in order to construct my black hole solution. If I chose a different setup, I get a different black hole. So this is a black hole such that the asymptopia are flat, and the geometry near the black hole horizon turns out to be ADS3 cross S3. It's a particular black hole in string theory I'm studying. Other black holes that one could study. So as you see, I haven't gone through any of the details, so this is just a rough story that I'm giving you. But I can sort of, let me make one other comment, that the black holes I'm studying in type 2a, I can equally study in type 2b by applying dualities. So 10-dimensional string theory, type 2a string theory, compactified on a circle of radius r, is the same as 10-dimensional type 2b string theory, compactified on a circle of radius alpha prime over r. So the two theories are what are called T-dual. So they lead to the same physics in 9 dimensions when you do either of these compactifications. So this is convenient, and it means you can map type 2a string theory to type 2b string theory. Type 2b string theory is sometimes more convenient as a description of these systems. So if we do, so I'm going to call my y direction x5, and I'm going to call my t4 x6 through x9. If I do a t-duality on x6, then I have a system of f1 and s5 and p. At this time, I'm in type 2b. Okay. If I then do, so this is t6. If I then do an s-duality, this f1 string becomes a d1 brane, this ns5 becomes a d5, and the p stays a p. So now I've got a d1, d5 p system in type 2b. Because d1 and d5 differ by 4 spatial dimensions, this is a supersymmetric configuration. It turns out when d-branes, when you consider bound states of d-branes, where the difference is 4, you preserve supersymmetry. It's a fact of string theory. Okay? So this is still supersymmetric. The same black hole I'm studying, I'm just studying this black hole in a different duality frame. Now, to answer, I think Gary's question previously, I can permute these charges by using other S and T dualities. Okay? So in the tutorial today, we'll see how to permute this, for example, to a different set of charges. For example, I can write this as P F1 and S5 via these S and T dualities. Okay? So we'll see how to do that later today. Okay, so I want to construct some microscopic counting of this entropy in order to appreciate where it comes from statistical physics rather than thermodynamics. So this is why we had that mathematical aside last time on the Hardy formula. So let's just look at the system with two charges. Okay? For the system with two charges, we have an F1P downstate. It turns out that the mass squared associated to a downstate like this is 2 pi r tension n1 plus np over r squared plus 8 pi t n r. N r is the number of right movers in our theory. But this is the same as 2 pi r t n1 minus np over r plus 8 pi t nl, stable level matching basically. So, in order to preserve supersymmetry, nr equals 0, and we can solve for the mass when this happens. So the mass turns out to be 2 pi r t n1 plus np over r. So we just take nr equals 0 to the square root of both sides to get this expression. And it turns out that 8 pi t nl minus n1 np equals 0, which tells us that nl is n1 np. Okay? So, let's let n1 and np be large numbers. If n1 and np are large numbers, nl is a large number. Now, remember I compactified on S, so the branes are wrapping S1 cross T4 in our set. So, they can oscillate in 8 directions. So there's just an F1 string wrapping the S1. That F1 string can oscillate in the torus directions, or it can oscillate in the macroscopic directions. So there are 8 oscillatory modes for each of these NLs. So 8 oscillatory modes means there are 8 bosonic operators, 8 bosonic harmonic oscillators if you like, and 8 fermionic harmonic oscillators. The central charge of bosonic CFT is 1. The central charge of a fermionic CFT is 1/2. So 8 plus 1/2 times 8, which is 12. Okay? So the central charge here for the oscillations is 8 plus 1/2 times 8, which is 12. So Hardy's formula tells us the number of states is the exponential 2 pi square root c nl over 6. And this works out to be e to the 2 pi, e to the 2 square root 2 pi square root n1 n5. Now you can think about this setting as a 3-charged black hole with a single NS5. So let's promote this to 3 charges. So let's let n5 equal 1 for the time being. That way, NL is still going to be n1 times np. Because there's only one brane. But now, we can no longer oscillate, the F1 string has to oscillate in the rolled volume of the NS5 brane. So instead of 8 degrees of freedom, there are now 4 degrees of freedom for the oscillations. So, C equals 4 plus 1/2 times 4, which equals 6. You plug that into the Hardy formula with the same NL, and you find the entropy, S, is 2 pi square root n1 n5. Sorry, n1 np. But I've chosen n5 equals 1. But I know from duality that this result must be symmetric under these charges. So my answer has got to be 2 pi square root n1 np n5. So the Hardy formula calculation gives us the same entropy we found in the gravity theory. 2 sides match. Okay. So what I'm doing is I'm doing a string calculation here with a metric in order to get an area and convert the area to an entropy. Then I imagine how many ways there are of partitioning energy among n1 N5, and NP. Number of ways of doing that is a partition problem solved for us in a large so when number of degrees of freedom is large, we can apply the Carty formula to count the number of degrees of freedom, and we get the same answer. Okay? So this is some microscopic enumeration of entropy, which recovers the area that we saw in classical gravity. Okay, so this is some weak coupling sort of argument. Lunan and Thor made these arguments precise. This guy here was the guy who invented this program, basically. Made these ideas precise by constructing explicit microstates in a strong coupling regime. So here, this is basically the Schrödinger-Wolfman counting that I showed you. It's a weak coupling counting. Because things are supersymmetric, the weak coupling counting is the same as the strong coupling counting. These operators are what are called protected. They don't change under changing the energy scale of the theory. They don't renormalize, in other words. So the weak coupling counting is the same as the strong coupling counting. That's good enough to compute for us the entropy, but that's not good enough to tell us what the black hole microstates are in the regime where the black hole actually exists. So Lunan and Thor figured out how to construct these explicit microstates, and they wrote down metrics for this. I won't explain this in detail, but I want to give you some heuristic picture of what's going on. Okay. So what Lunan and Thor found is there are, for the D1, D5 system, they found that there are e to the entropy microstates with the same charges as the black hole. So in other words, the e to the s black hole metrics they can write down the same global charges as the black hole we're considering. So let me show you a picture. Illustrates the point. So we've got flat space. This is classically. And the metric looks like this. Somewhere in here, there's an ADS near horizon region, and then we get the horizon. Somewhere here is a singularity. And the entropy is the area over 4G, where the area is the area of this horizon. Okay. This is the semi-classical picture of a black hole. So the quantum picture that Lunan and Thor propose is the following. You again have flat space, and you again have an ADS throw, and this is where the horizon would have been in classical theory. But now, instead of having a horizon there, you have a smooth geometry there. In fact, you have many smooth geometries. Smooth geometries you have all look different. The number of ways of writing down smooth geometries accounts for the entropy. So you have different ways of capping this region. So all of these different ways of capping the region are differing from each other at the scale of the horizon. Okay? Each of these space-times doesn't have a horizon or a singularity. They're smooth geometries, they're regular geometries. They're not topological. It turns out that, okay, so let me make a few observations about this later. This is the so-called fuzzball picture of a black hole. Each of these ways of capping the geometry is called a particular fuzzball. So, the number of ways of capping the geometry is e to the s Bekenstein-Hawking. That's the microscopic origin of the black hole entropy in the story. Okay. So all of these geometries have the same charges as the black hole. So let me make some observations about this. Yes?
What would limit the different ways of constructing those smooth geometries? Why didn't the black hole include it? Because I'm just thinking,
These are fixed by the charges.
the charge of the black hole.
The N1, N5, and P charges of this solution. So the first point is there are many horizon-free, singularity-free solutions in supergravity with the same charges as black hole. They differ, they're the same metric, roughly up until this, where the horizon would have been, and they differ afterwards. That's the first observation we want to make. The second observation is that the supergravity is only good for some fraction of these states, for some fraction of these microstates. What this means is that for most states, the notion of geometry ceases to make sense here. There are large Planck scale curvatures, for example, that extend all the way out to this horizon scale. So it's only very few states for which supergravity is a good description of the cap region. But in any case, there are lots of states. None of these states have singularities or horizons. They're all regular geometries. So a typical state is characteristically stringy all the way to the effective horizon. Which tells us there's a new scale in quantum gravity. So we discussed last time that a solution to the information paradox might be that there is information encoded within a Planck distance of the singularity. That's not what these guys are showing. They're saying the information extends all the way to the horizon scale. So the new scale in supergravity, in quantum gravity, is n to the alpha times n quantum, where n is some large number. N, roughly speaking, scales like n1, n5, np to some power. Okay. So this n1, this basically scales like the horizon scale. That's a new scale we have in the game. So in the classical theory, we can recover if you're in a microstate in this room, for example, you consider a microstate of the gas molecules in this room, you can recover the thermodynamics by doing an averaging over all the possible microstates. That's what the canonical ensemble does, for example. It weights microstates by a Boltzmann factor, it does an averaging over all the possible states of the system. So if you do a thermodynamic averaging in the same manner on these states, the geometry you recover is this. This singularity and the horizon are effective concepts that result from this averaging process. So the horizon singularities arise from this coarse graining, this thermodynamic averaging we do. Then, like the black hole, if we scale up G Newton, we solve the Schwarzschild radius proportional to G Newton. If we make G Newton bigger, these microstates also grow. Just like a black hole grows if you make G Newton bigger. So the counterintuitive behavior in which the system becomes bigger with increasing Newton constant is emulated by these microstates. Whereas most systems of gravity we know become smaller and make Newton coupling stronger. We can as well, so I told you the near horizon here has an ADS region. Because it has an ADS region, the gauge gravity correspondence tells us we express these microstates in terms of CFT. In this case, it's CFT2, since this region is ADS3 plus S3. So, we can write down microstates in CFT2 that account for this entropy. For the D1, D5 system, the 2-charged black hole, we can write down all the microstates. For the 3-charged black hole, we can write down some fraction of the microstates, and people argue about what the correct fraction we've written down is. Up until a few years ago, it was some charge to the 5/4 power, whereas we needed Q to the 3/2 to account for the entropy, because the entropy is scaling by square root n1, n5, nt. Now, recently, as in the last year or so, people now claim to get the entire accounting up to some numerical factor, to get the right scaling in Q. The guys who do this are Bena and Warner and Justo and Russo and Shigemori. So Russo, one of the guys who did this, will be here in about 2 weeks to give us a colloquium. And hopefully he'll talk about some of this stuff maybe. So, one other point is that although supersymmetry was used for the first microstate constructions, we've since constructed microstates that don't require supersymmetry. We haven't constructed enough microstates to account for the entropy, but in principle, the same sort of story would go through because you construct the states sort of like this. This was, in fact, work I did about a decade ago with Simon Wallace and the students at Durham to construct these microstates without supersymmetry. So the story seems to be a story which is coherent. We don't know if it's a final answer, but it at least explains the entropy of certain black holes in string theory. There's another recent argument, 2012, by Merol, Polchinski, and Soy, that there is a firewall you associate to an infalling observer near the black hole horizon. This again suggests there's a new scale of quantum gravity that goes like the horizon scale for these black holes. But this firewall story is consistent with the microstate picture of a black hole. Now, the metrics for these guys involve some functions which basically describe a profile of the string. And this profile function needs to be quantized in order to get either the S black hole solutions here. That's also been done for the 2-charge case. Okay. So all the story is a story which tries to explain the entropy of certain black holes in string theory microscopically. Whenever you have an entropy, the question you need to ask yourself is, what are you counting? What are the quantum states of your system? We can answer that for a particular class of black holes. This class of black holes is generically supersymmetric, but there are non-supersymmetric modifications in the story where you can construct some microstates anyway, although not enough microstates to account for the entropy. Figuring out the entropy of the Schwarzschild black hole in string theory is a work in progress. We really don't know what to do. That's an open problem that all of you are invited to work on. We see that we're learning a lot about gravity in string, and we're learning a lot about what the meaning of entropy is in gravitational systems. We're seeing these gravitational systems, and entropy is codimension 1, described by CFT variables in 1 dimension lower than the dimension of the space-time. We're seeing these as general lessons, but the details are still missing in many cases. And as a result, it's a very exciting area to be working in, and hopefully we'll make progress in the next years. So again, consider this an invitation to work on physics of this nature, because I think we're learning something very profound, very beautiful, and very important about the structure of gravity and the emergence of space-time. So I'll stop there. Thank you. Any questions? Yeah.
What's the fundamental difference between the ABS and the Schwarzschild that enabled us to count the microstates of the ABS compared with the
So here, the story is really predicated on having supersymmetry initially. Because of supersymmetry, we're able to count microstates explicitly. Now, we can break supersymmetry and construct some microstates. We don't really know how to construct all the microstates without supersymmetry. Schwarzschild black holes were examples of black holes without supersymmetry. So they were hard.
I think it was too quick for me to connect the partition of integer and counting the microstates from the mass where you mentioned. Last time we showed how the asymptotic formula, and then I just want to know because it was
Yeah, I'll show you the tutorial in more detail. But the idea is that the Cardi formula lets us count on a partition large numbers. So what I'm doing is I'm mapping this problem to a partition problem. I'm getting a large number of oscillators, distributing energy among these oscillators. The number of ways of doing that is a partition problem whose asymptotic answer is given to us by the Cardi formula. Yeah. Other questions? No, I realize I haven't gone through many of the details. I just want to convey this heuristic picture, this impressionistic picture of what's going on. So please ask questions about this picture if you have any, now or in the tutorial.